Okay, for this part, we're looking at solving a system of equations by using an inverse matrix. And let's say we have for a given system, it says to use an inverse matrix to solve the following system. And for this system, I have in the variables x and y. Okay, so I have that 2x plus 4y is equal to 11. And we have also that 3x minus 2y is equal to 1/2. Okay, and we're looking at the values of x and y that will fit into both of these equations. All right, and we have just for the setup in determining the inverse matrix. Okay, so you have the coefficient matrix A times X is equal to B, and B is going to consist of, again, the constants to which the respective equations will be set equal. And so if AX is equal to B, okay, we're going to have that X is equal to the inverse of matrix A times B. And let me mention, okay, so for X, it's not the variable X like in the X, Y coordinate system. X is just going to be the general case of what we have for the solution matrix. Okay, so for A times the solution matrix of X is equal to B, okay, if I fill in, so for A, this will be the coefficient elements of what we have for the X and the Y terms. Okay, so you have from the first equation, have like 2 for 2X, 4 for 4Y. Bottom row, we have 3 for 3x and negative 2 for minus 2y in the second equation. And the solution matrix X, again, this consists of the variables we are looking at solving for. So you have X and Y contained. And again, for B, I have 11 and 1/2. Okay, and let me mention, okay, so recall, okay, so again, you have 2x and 3x, 4y, negative 2y. So just looking at it, like if I were to multiply and just break it up, so you have like x times the first column portion of the coefficient matrix. I have like x times 2 and 3, and then I have plus y times the second column portion of the coefficient matrix. I have 4 and negative 2, so I have like 2x, 3x, and again 4y and negative 2y. And looking at what we have and working with A, okay, so again, going back to the determination of the inverse matrix, and recall the formula. A times the identity is equal to the identity times the inverse. So setting things up here, okay, so I got 2, 4, 3, negative 2 from A. And with the two equation system, again, the identity matrix will be a 2 by 2 arrangement. So I have 1, 0, 0, 1. And again, I'm going to be performing the Gauss-Jordan elimination. And so I want the first element, that is the top row, top portion, top row, first column, value to be at 1. And what I haven't set is 2. Okay, so I can change the 2 to a 1. So I can just take 1/2 of the first row. So that is going to be transformed to 1, 2, 1/2, and 0. Now, what I want, okay, is that for the reduced row echelon form, okay, I want the first column to consist exclusively of 1 and 0. But now I got the 3 at the bottom, and I can just change this to a 0 by performing the operation where I can take the second row elements and deduct 3 times the corresponding first row elements. Okay, so we have 3 minus 3, negative 2 minus 3 times 2, 0 minus 3/2, so made that 0 minus 3 times 1/2, and 1 minus 3 times 0. So I have, in the change up, I have 0, negative 8, negative 3/2, and 1. Now for the first column, I have 1, 0. And the second column, I want 0 and 1. And I can change the negative 8 that I have momentarily to 1. Okay, so I'm going to divide by negative 8, or take negative 1/8 of the second row elements. So when having the change up, I'm going to have 0, positive 1, positive 3/16, and negative 1/8. So I got 1, 0, and I had the desired 1 at the bottom of the second column, but I want to change that to immediately above to 0. So looking at what we have here, I can change the 2 to 0 through the process of taking the first row elements and deducting twice the corresponding second row elements. So we have 1 minus 2 times 0 is 1. 2 minus 2 times 1 is 0. And 1/2, and what's going to be minus 3/8, that's going to be a positive 1/8. And what's going to be 0 minus twice of negative 1/8, that's going to be 0 plus 1/4. And guess what? With the follow through, okay, so I have this time the identity matrix elements on the left, and for what I have to the right are going to be the elements of the inverse of matrix A, and the inverse is going to consist of 1/8 and 1/4 in the top row, 3/16 and negative 1/8 at the bottom. And now just going back to our formula where x is equal to the inverse of A times B. Again, the inverse of A, we have 1/8, 1/4, as well as 3/16 and negative 1/8. And again, B happen to consist of the constants to which the first and second equations were set equal. So I have 11 from the first equation, 1/2 from the second. And looking at multiplying together, okay, so we have 11 times the first column elements from the inverse, and a half plus 1/2 times the second column elements. So looking at what we have at the top, so we have 11/8 plus 1/8 is going to be 12/8, and that will be reducible to 3/2. 11 times 3/16 is going to be 33/16. And we have 1/2 times negative 1/8 is going to be a minus 1/16. So I have 33/16 minus 1/16 will be 32/16, which is going to be equal to 2. So again, this x is in reference to the solution matrix, where we have the variables contained to be x and y from the equations, and x is equal to simultaneously 3/2 and 2, and looking at mapping together. So x refers to 3/2, and y likewise refers to 2. And so we have for this system of equations, x is equal to 3/2, and we had that y is equal to 2. Now let's say that if I move to a 3-equation system, and for this one we have x plus y plus z is equal to 9, and we will have that y minus z is equal to negative 2, and we have x plus z is equal to 6. Now b is going to consist of the numbers 9, negative 2, 6. A is going to be like 1, 1, and 1 for the first row, and since I do not have a leading x term in the second equation, I'm going to have 0, 1, negative 1. And then for the bottom row, I'm going to have 1, and then 0 since I have a void of a y term in the last equation, and then I have followed by 1 in reference to 1z. So setting up what we have for ax is equal to b. Again, where x here is going to be the solution matrix, where inside we have in reference to the letters x, y, and z. So again, we have a, okay, to consist of 1, 1, 1, 0, 1, negative 1, 1, 0, 1. And again, for the solution matrix x, we have contained the solution variables x, y, and z. And once again, b consisting of 9, negative 2, and 6. So looking at setting things up and taking the inverse of matrix A. So again, going back to our algorithm, A times I is equal to I times the inverse of A. So we got the AI set up. Okay, so first column, I want to have 1, 0, and 0. So I got the 1 and 0 part, and the bottom 1 from the first column, I'm going to change over to 0. And that can be done by taking from the last row the first row element. So you have 1 minus 1 is 0. And then for the follow through, you got 0 minus 1, 1 minus 1, 0 minus 1, 0 minus 0, and 1 minus 0. Okay, so I got 1, 0, 0. Now for the second column, I want 0, 1, and 0. So I'm going to change the 1 in the second column, top row to 0, by deducting the second row elements from the corresponding first row elements. And doing so, I'm going to have 1, 0, 2, 1, negative 1, 0. And to change the negative 1 at the bottom of the second column to 0, I'm just going to add the second row elements to the third row elements. So I got 0 plus 0, negative 1 plus 1, 0 plus negative 1, and then I have negative 1 plus 0, 0 plus 1, and 1 plus 0. So this is what I have at this stage. And okay, so I got the first column 1, 0, 0, then I have 0, 1, 0, And then I want the third and last column to work with to consist of 0, 0, and 1. Okay, but for what I have at the bottom of the third column, I have -1, and I want to change that over to a +1. So I'll just be taking the opposite sign of the third row elements. So I have 0, 0, 1, followed by 1, -1, and -1. So changing over the 2 and the -1 from the third column to 0, I'm going to deduct twice the third row elements from the corresponding first row. So in this case, I'll end up with 1, 0, 0, -1, 1, and 2, and then adding the third row elements to the corresponding second row elements. Okay, so we have 0, 1, 0, 1, and then I have 0 and -1. And guess what? For what I have for the first three columns, I have 1s running diagonally, and immediately I have 0s above and below. And okay, so that is our identity matrix formation elements. And for the last three columns, those will consist of the elements that will define what we have for the inverse matrix. So the inverse of A, we have to consist of -1, 1, 2, 1, 0, -1, and then we have for the bottom row, we have 1, -1, and -1. And again, for the solution matrix, that is going to be equal to the inverse of A times B. So I got the inverse of A elements. B, again, we have with 9, -2, and 6. And then so for the solution matrix X, okay, so we have 9 times the first column elements from A's inverse. Then I have -2 times the second column elements, and then have +6 times the third and last column elements from the inverse of A. And so we have at the top, so we have -9 -2, which would be -11, and then I have +6 times 2 is 12, so I have 1. Then for the middle, we have 9 -0 is 9. 6 times -1 is -6, and 9 minus 6 is 3. Then I have 9 -2 times -1. That's going to be 9 plus 2, which is 11. And then 6 times -1 is -6, and 11 minus 6 is 5. So the solution matrix X consists of 1, 3, and 5. And again, the solution matrix will be in reference to the solution variables X, Y, and Z from the system of equations. So you have X is equal to the containing of X, Y, and Z. And again, we have is equal to 1, 3, and 5. And mapping the corresponding parts. So X refers to 1, Y refers to 3, and Z is going to be with respect to 5. And so we have for the solution variables, okay, we're going to have that X is equal to 1, Y is equal to 3, and we have that Z is equal to 5.